Let's talk about memory in more detail. AI workloads are often memory-bound rather than compute-bound. That means the speed of training or inference is limited not by how fast you can compute multiplications, but by how fast you can feed data into the compute units. Modern accelerators use high-bandwidth memory, often stacked on the same package as the compute die. This reduces latency and increases bandwidth compared to traditional off-package memory. High-bandwidth memory uses wide buses and 3D stacking to provide hundreds or even thousands of gigabytes per second of bandwidth. This is critical when you are streaming large matrices into tensor cores or systolic arrays. However, even high-bandwidth memory is limited compared to on-chip SRAM. So accelerator design involves careful trade-offs between compute units, on-chip memory size, and off-chip memory bandwidth. Another important concept is the roofline model. The roofline model is a performance model that relates compute throughput and memory bandwidth. It helps you understand whether a workload is compute-bound or memory-bound. If your arithmetic intensity, meaning the ratio of operations to bytes moved, is high, then you are likely compute-bound. If it is low, you are likely memory-bound. Hardware accelerators are optimized to push the roofline as high as possible, but software must also structure computation to increase arithmetic intensity. Now let's discuss inference versus training. Training is typically much more computationally intensive. It involves forward passes, backward passes, and weight updates. Backpropagation roughly doubles or triples the computational cost compared to inference alone. Training also requires storing intermediate activations for the backward pass, which increases memory pressure. Therefore, training accelerators are optimized for high throughput and large memory capacity. Inference, on the other hand, often has stricter latency constraints. For example, in an interactive system like a chatbot, users expect responses within seconds or less. Inference workloads may use smaller batch sizes or even batch size 1. This reduces parallelism and changes the performance characteristics. Therefore, some accelerators are specifically optimized for inference, focusing on low latency, high efficiency, and aggressive quantization support. Edge devices present yet another scenario. On a smartphone or IoT device, you have severe power and thermal constraints. You cannot dissipate hundreds of watts like in a data center. Therefore, mobile AI accelerators are integrated into system-on-chip designs. These accelerators are designed to perform neural network inference with minimal energy per operation. They often use fixed function units and support low-precision arithmetic to maximize efficiency. From a software perspective, hardware accelerators are exposed through programming models and libraries. You rarely program a tensor core directly at the register level. Instead, you use frameworks like PyTorch or TensorFlow, which generate kernels that run on the accelerator. Under the hood, these frameworks rely on highly optimized libraries that map high-level operations to hardware primitives. Compiler technology plays a crucial role. Compilers for AI accelerators must perform operator fusion, memory planning, tiling, and scheduling. Tiling is especially important. When multiplying large matrices, you break them into smaller tiles that fit into fast memory. The compiler orchestrates the movement of tiles between memory levels and schedules compute operations to maximize reuse and minimize stalls. The trend in AI hardware has been toward domain-specific architectures. Instead of building one general-purpose chip that tries to do everything reasonably well, designers build chips that are extremely good at one class of workloads. This is justified by the economic scale of AI. If you are going to deploy millions of accelerators for training and inference, even small efficiency gains translate into massive cost savings. Energy efficiency is arguably the most critical metric. The limiting factor in scaling AI systems is not just transistor count but power consumption. Data centers have finite power budgets. Each watt consumed must be cooled, and cooling itself consumes energy. Therefore, the metric of interest is often performance per watt rather than absolute performance. Hardware accelerators aim to maximize operations per joule. Let's connect this to model scaling laws. As models grow larger, the compute required for training grows superlinearly. Training frontier models requires enormous clusters of accelerators running for weeks or months. the cost is dominated by hardware and energy. Therefore, improvements in accelerator design directly enable the training of larger and more capable models. In that sense, AI progress is tightly coupled to hardware progress. Another interesting development is sparsity support. Many neural networks contain redundant parameters. If you can exploit sparsity, meaning many weights are zero or near zero, you can skip certain multiplications. Some accelerators include hardware support for sparse matrix operations, which can increase effective throughput. However, sparsity is challenging to exploit efficiently, and it requires coordination between model design, training procedures, and hardware capabilities. We should also mention reconfigurable hardware, such as field programmable gate arrays, or FPGAs. FPGAs allow you to configure hardware logic after manufacturing. They are less efficient than ASICs but more flexible. In some inference scenarios, FPGAs are used to implement custom data paths optimized for specific models. However, the programming complexity is higher, and the performance per watt is usually lower than specialized ASICs. As we look to the future, chip design is increasingly constrained by physical limits. Transistor scaling is slowing down. Instead of relying purely on smaller transistors, designers use architectural innovations, 3D stacking, chiplets, and advanced packaging. Chiplets allow multiple smaller dies to be connected on a single package, improving yield and scalability. Advanced interconnect technologies allow high-bandwidth communication between chiplets. Another emerging theme is memory-centric computing. Because data movement is so expensive, some research explores moving compute closer to memory or even into memory. Processing in memory architectures attempt to perform simple operations where the data resides, reducing the need to shuttle data back and forth. While still largely experimental, these ideas reflect the central importance of memory in AI workloads. Security and reliability also matter. Training large models for weeks means hardware must be robust to failures. Accelerator clusters include redundancy and fault tolerance mechanisms. Soft errors due to cosmic rays or voltage fluctuations can corrupt computations. Error correction codes and checkpointing strategies are used to mitigate these risks. Finally, we should reflect on the co-design principle. The most powerful AI systems today are the result of hardware-software co-design. Model architectures are chosen with hardware characteristics in mind. For example, the dominance of dense linear algebra in transformer models aligns well with matrix multiplication hardware. Conversely, hardware designers optimize for the operations that dominate state-of-the-art models. This feedback loop accelerates both hardware and model innovation. If you walk away with a mental model, it should be this: AI hardware accelerators exist to maximize the number of useful numeric operations per unit time and per unit energy, while minimizing the cost of moving data. They achieve this through massive parallelism, specialized compute units like tensor cores or systolic arrays, hierarchical memory systems, reduced precision arithmetic, and high-speed interconnects for distributed scaling. Understanding these principles allows you to reason about performance bottlenecks, cost trade-offs, and scaling limits in AI systems. It also clarifies why certain model architectures are popular, why distributed training is complex, and why hardware innovation remains central to the future of artificial intelligence.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.